Welcome to our class online. I'll walk you through the material for this week in a movie. Today's story is 2 Ways to Count to 10, retold by Ruby D. I'll read it in a separate movie, so you can stop this one now and listen, or listen to it later. What do we mean by conceptual knowledge? Van der Waal talks about it frequently in the text, and it's important that you understand what he means. If you look at this large object in the center of the screen, I asked you to identify it, you would probably say half a circle. If I pointed to the smaller object on the screen, you would identify it as a quarter circle or 1/4 of a circle, and you'd be correct. Now if I told you that the larger of the 2 objects was a whole, you would accurately name the smaller of the 2 objects as half. That's because you have conceptual knowledge of fractions. You understand that fractions are relational. Many of the students in your class would insist that the larger object is a half and the smaller is a fourth, no matter what you call a whole. It's because their understanding is incomplete. They don't see the relationship. Now let's define number sense. It is a confusing concept. If you were to put these blue objects in front of a 5-year-old and ask them how many there were, you would get a variety of answers depending on the 5-year-old. One might say that they have no idea. Another one might count the objects like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Counting several of the dots more than once. Then another might have good one-to-one correspondence and count each of the dots, perhaps even moving the objects as they're counted. That child would know that the number stated represents the total objects counted up to that point, and not just a word that's part of a series. That's part of number sense, although it involves much more relational thinking about number. We take number sense for granted. Few of us remember what it was like not to know how many. While we're defining, let's look at number and numeral. A numeral, like 3, is a symbol that represents an amount, like the 3 blocks that you see here. Number means how many items in a collection. So at the bottom of the screen, you see both the number in the grid and the numeral 1 to the left of the grid. Now we're going to go through the Math Recovery Learning Framework in number. This is important whether you're teaching preschoolers or middle schoolers, because your students will lie somewhere along this continuum, and it will be important for you to recognize both where they are and where they need to go. Stage 1 is emergent counting. This is the child who looked at the blue dots on the previous slide and couldn't count them, either because he or she didn't know the counting words or because they didn't have one-to-one correspondence and counted more or fewer dots than actually existed. Stage 1 is perceptual counting. The child at this level knows the number words and can count accurately as long as they can see the objects. So given 7 blocks, the child can look at them, not necessarily needing to touch them, and count them accurately. In stage 2, the child can count items in a screen collection. In other words, I show the child 4 blocks, cover them with a card, and then put 3 blocks down. When I ask the child how many blocks, the child would touch or look at the card and count 1, 2, 3, 4, and then count 5, 6, 7. Stage 3 is where the child is able to count on. If you show them a set of 4 objects and then add 3 more, they will start counting at 4, 5, 6, 7. This child can solve written problems by counting up or back for addition and subtraction. They can think of numbers as a composite group. In other words, they can see 5 as well as 5 ones. Now this stage usually occurs at first grade, but a lot of students get stuck here sometimes because they're encouraged to count on so much in school that they don't get beyond it. Stage 4 has the child using the most efficient counting strategy to solve problems. That may be counting up or backwards depending on the number. This child understands part whole, which is a very important mathematical concept. Or part whole, I should say. It means that within the number 7, there are other numbers like 4 and 3, or 5 and 2, or 6 and 1, and all those combinations equal 7. Now stage 5 is where you want your student to be. This child can solve both addition and subtraction problems using non-counting strategies. This is where students remember combinations that make a number, or no-number facts, or can partition numbers, or use doubles, and focus on the relationship among those numbers and operations. This child knows that 3 plus 2 equals 5, as does 2 plus 3. They understand properties like commutativity, associativity, and are able to develop growing number patterns. These are not the kids that you are worried about in your classroom. Now it's important to note that there are students who are in middle school who are stuck in some of the previous levels for a variety of reasons. In order to move forward mathematically with understanding, they will need to have some support to develop the concepts that they are lacking. Now let's look at base 10 development. Many educators worry that too early a use of base 10 blocks can confuse young children. At level 1, the child concentrates on the units that make up 10. They don't see 10 as any kind of unit. Level 2, children see 10 as a unit composed of 10 ones. By this time, using base 10 blocks can be helpful to children, and they can solve problems using double-digit numbers using those manipulatives. Level 3 children need no materials or representations, like pictures of base 10 blocks or stamps of them. These children can solve addition and subtraction tasks without materials because they understand that the 2 in 21 is different from the 2 in 32. Now, imagine that you have some paper blocks like these without the grids. They are base 5 blocks. I used the grids to make sure that they were accurate. Let's look at 2 activities. In the first, you would make a collection of 2 large squares, 3 strips, and 4 units. And then another collection of 1 large square, 4 strips, and 3 units. If I asked you to combine the 2 collections in the simplest way, or show the total amount, you would be able to recognize that it takes 5 units to make 1 strip and 5 strips to make 1 square, and so you would combine them, taking the 7 units and trading them for 1 strip, 2 units left over, taking the 7 strips you already have and adding that new strip, and trading that for 1 square and 3 strips left over. Then you would have 4 squares, 3 strips, and 2 units as the simplest form of the combination of the 2 groups. In the second activity, with the base 5 material, you could play a game where you would divide a paper into 3 parts, squares, strips, and units, and you would roll a dice and play a trading game. You would gather as many units as the pips, that's what the dots on the dice are called, but in the directions I give, I would say that when you get 7 units, you can trade them for a strip. When you have 7 strips, you can trade them for a square, and you win. Now this activity would be more difficult because looking at the materials confuses you, because looking at them, you see 5 units equals a strip, and 5 strips equal a square. How are the activities alike? Well, they both use the same materials and they both use trading. How are they different? In the first activity, the strips are a model for the relationship. In the second, you were confused because the material did not model the actual relationship among the pieces. It's so important to use the right materials when you are teaching children. Here's a game that you can play alone or with someone. Fill a bowl with 20 objects like papers, clips, pennies, that kind of a thing. Then roll one die and empty the bowl as you do by the number you have rolled. So if you roll a 5, you remove 5 objects from the bowl. Record your work. For example, 20 minus 5 equals 15. See how many rolls it takes to empty the bowl. Why couldn't it be emptied in 1 roll or 2? These are questions you'd ask students if you played the game with them. What's the greatest number of rolls it could take, or the fewest? Play 5 games and look at your results. What mathematical issues did you have to take into account and think about when you were playing the game? Here's another game to play. Try it alone or with your family or friends. You need a sheet of paper and columns for 10s and 1s. You roll one die and can put the numeral of that roll in either the 10s or 1s place for each turn. You get 6 rolls to get the total equal to 100 without going over. Again, what did you have to think about to be successful at this game? Isn't it interesting that students would be practicing their math computation without doing a time test or a worksheet? One last activity before we take a break, drawing stars. Predict how many stars you can draw in 1 minute. Write your prediction down. By the way, I always have children write their predictions in pen or marker, otherwise they change it. They need to be right. Then set a timer on your cell phone or have someone time you and draw stars for 1 minute. Then count your stars. It's interesting to look at how you do that. By 1s, 2s, groups of 5 or 10, it will be informative to see how your students do this activity as well. Now let's take a break, and in the part 2 of the movie, we'll continue talking about arithmetic.